D is a operator is a partial differential operator with matrix coefficients. And similar, if we take another meromorphic function mu, then here mu, then we have similar identity. D of mu psi is equal to mu psi. And from this two identity, we have that vector function psi belongs to the kernel of the commutator. And since our model is free from this identity, we obtain that d lambda commutes with d mu. So this is a construction idea of Nakayashi, and he constructs explicitly such model M. Let me explain his construction. Let's take abelian variety. Here, omega is a symmetric G times G matrix with positively defined imaginary pattern. Let me recall that theta, Riemann theta functions is defined by this identity. And theta functions satisfy this periodicity condition. And Nakayashi introduced the following set of functions. It consists of functions of the following form: f of zx multiplied by this exponential function. Here, f of zx has a pole on theta divisor, and f satisfies this periodicity condition. And the theorem of Nakayashi is the following: if theta divisor is non-singular and C is not equal to 0, then MC is a free DG model of rank G factorial. So, and this theorem gives us an example of commuting partial differential operators with matrix coefficients such that common eigenfunctions and eigenvalues are parameterized by abelian variety. Well, for example, if we take the case when the dimension of our abelian variety is equal to 2, then Baker-Heiser model can be generated by these two functions. Here, C prime is some vector. And one can construct explicitly corresponding operators.
Sorry, and in that James 2 case, is there any geometrical meaning of x and z?
X are our variable x1 and x2. Our partial differential operators are operators with respect to x1 and x2. And z is a point of abelian variety.
Okay.
That is a spectral parameter. It belongs to abelian variety. Another example, if we take k shifted theta divisors, and let's consider intersection of this shifted theta divisor. And under some conditions, I don't want to explain these conditions, it's not important for us. And if we restrict our elements from Baker-Heiser module to this algebraic variety y, and let Q is intersection of our variety y with theta divisor, then it turns out that this module over ring of partial differential operator with respect in variable x1 x g minus k also is free module. And this theorem also gives us an example of free Baker-Heiser module. And of course, it also gives us example of commuting partial differential operator. This is my old result. Okay, now let's go to the commuting difference operators. I also would like to start with one-dimensional case. Let us assume that we have two difference operator, Lk and Ls. Here, T is a shift operator, Tx on function f of n as with the help of this formula, Tfn is equal to Fn plus 1. And Uj of n are some coefficients. And commutativity condition of these two operators is very complicated system of nonlinear partial nonlinear difference equations. And what we know about commuting difference operators. First of all, there is an analog of Borsnow-Chowdy lemma. If two operators commute, that there is a polynomial f of z and w such that f Lk Ls is equal to 0. And this polynomial defines a spectral curve. And this spectral curve parameterize common eigenfunctions and eigenvalues of commuting difference operators. And any commutative ring of ordinary differential operators is always isomorphic to a ring of meromorphic function on spectral curve with unique pole. But in difference case, situation is the following. Any commutative ring of difference operators is isomorphic to a ring of meromorphic function on spectral curve with m poles. And such operators are called endpoint operators. In the case of two-point operators of rank, when rank means rank is a space of a dimensional space of common eigenfunctions with fixed general point on spectral curve. Rank 1 means that if you fix a point on spectral curve, then there is a unique common eigenfunction up to multiplication by constant. So, in the case of two-point operators of rank 1, such operators were found independently by Krichyver and Mumford. And such operators can be expressed in terms of theta function of Jacobi variety of spectral curve. And spectral curve, spectral data for one-point operators of rank greater than 1 were obtained by Krichyver and Novikov. Let me explain briefly our result with Gulnara Maulesheva. This is a new class of commuting difference operator. Let's take a Riemann surface gamma of genus G, gamma 1, gamma G are fixed point on gamma in general position, and Q is a fixed point on gamma, K minus 1 is a local parameter on gamma near point Q, and additionally we take a set of point Pn. N is an integer number, and we assume that Pn are in general position. Then there is a unique rational function which depends on n and point P of spectral curve, which has the following properties. If n greater than 0, then the divisor of zeros and poles of psi has the following form. It has zeros in point P1, Pn, poles in point gamma 1, gamma G, and pole of order n in point Q. And additionally, it has some zeros in point gamma 1, gamma G. And similar in the case when n less than 0. And the second condition, we assume that in the neighborhood of point Q, psi has the following asymptotic. Then, as I said, such function there is and unique. We call such function Baker-Heiser function. And if we take two meromorphic functions f and g on gamma, this unique pole in point Q, then similar to the differential case, we have two difference operators of such form with some coefficients u and v, such that lm psi is equal f psi and ls psi is equal to g psi. And these two operators, lm and ls, commute. And this is simple examples of our construction. If we take a hyperelliptic spectral curve and if we take point Q at infinity, we obtain this operator. Coefficients of this operator can be expressed in terms of cosinus and sinus. And this operator of order 2 commutes with operator of order 2g plus 1. And another example is the following. This operator of order 2 commutes with operator of order 2g plus 1. And here we see that coefficients of this operator of order 2 are polynomial in our discrete variable n. Okay, and now let me explain our construction with Nakayashi. This construction allows to construct commuting difference operator in several discrete variables with matrix coefficients. Let X be an algebraic variety and Y is a subvariety of X of codimension 1. And let us assume that we have the following set of functions. This set of functions depends on a discrete variable n belongs to z to the power g, and p belongs to is a point of our algebraic variety x. And we call this set M discrete Baker-Heiser model if the following conditions are satisfied. If we take a function psi from our model M, then if we take a shift of our discrete variable n with respect to ni, then this shift also belongs to M. We assume that condition 1 is satisfied. The second condition is the following. If we take arbitrary function f which depend only on n, then we assume that f psi also belong to M. And the second condition, the next condition is the following. If we take a meromorphic function lambda on our algebraic variety x with pole on y, then we assume that lambda psi belongs to M. And the last condition, the sum of any two elements from M belongs to M. So these four conditions means that M is a model over ring tau. Here K is a ring of functions which depend only on N, and T1, Tg are shift operator. Now let us assume that this module M is a free model over this ring tau. And additionally, we assume that this model is finitely generated. So it's generated by function psi1, psi(n). Then, similar as I explained in the differential case, if we take a meromorphic function on x with pole on y, then lambda psi we can represent it in the form d psi is equal to lambda psi. Here d is a operator, matrix operator. Components of this matrix operator belongs to this ring tau. And if we take another meromorphic function mu from our ring AY, we obtain the identity d mu psi is equal to mu psi. And similar from these two identity, we obtain that vector function psi belongs to the kernel of commutator d lambda d mu. And from the freeness of our model M, it follows that d lambda commutes with d mu. And our first example is the following. We take abelian variety X with a non-singular theta divisor. And let's take a union of MCM. Here, MCM can be represented in such form. What is written here? Theta A divided by M0 is a theta function with characteristic. The definition of this theta function with characteristic is given by this explicit formula. So Z belongs to our abelian variety, as similar to the differential case. C is a constant. X is a also constant or parameter. It's not important for us. N is a set of N belongs to ZG, and H is a set of parameters H1, Hg. It's not important for us. And K is a element of is a ring of functions depending only in H. And H we define this set. So, and it turns out that MC is a free module of over our ring tau J of rank G factorial. And this theorem allows us to construct an example of commutative ring of partial difference operators. For example, in the case of dimension 2, we can take the following basis in our free module. This is the explicit formula for the basis. And using this basis, one can construct explicit formulas for commuting difference operators. Components of the commutative operators can be expressed in terms of theta function. But I would like to explain how to obtain from this construction operators with rational coefficients. For this, it is necessary to use, instead of theta function, Weierstrass sigma function. More precisely, in the dimension 2, arbitrary abelian variety with non-singular theta divisor is a Jacobi variety of hyperelliptic curve of genus 2. And there is a very beautiful construction for Weierstrass sigma function. Viktor Matveevich Buchstaber with colleagues has many interesting results on such Weierstrass sigma function. So our abelian variety is a Jacobi variety of hyperelliptic spectral curve of such form. And it's turned out that if we consider, so our sigma function can be has Taylor series with respect to parameter C4, C3, C2, C1, and C0. And there is very beautiful, remarkable fact that if we substitute Z4, Z3, Z2, Z1, and Z0 instead of Cj0, then our Weierstrass sigma function has a remarkable limit. More precisely, sigma function becomes Schur function, and this Schur function is given by this explicit formula. Sigma is equal to Z1 to the power 3 divided by 3 minus Z to the Z2. And our function C1, C2 from the Baker-Heiser model also has a remarkable limit when C0 is equal to Cj is equal to 0. So instead of sigma, we have to replace this explicit polynomial, and instead of sigma 1, C1, C2, we obtain a rational function C1. I don't know this how to call this term, wedge maybe, C2 wedge, which are given by these two formulas. And sigma wedge is a Schur function. And it's turned out that coefficients for commuting partial differential operators in this limit becomes rational functions. More precisely, if we take meromorphic function lambda on our abelian variety, and in the limit, if we replace lambda in the limit, instead of lambda, we obtain the following rational function in Z1 and in the Z1 and Z2. Then we obtain the following partial difference operator, and coefficients of this partial difference of these difference operators are meromorphic function. And here I represent explicit formulas for this coefficients. Okay. So this is more or less the end. Okay, thank you very much for the attention.
Well, let's thank the speaker. Any questions on Zoom?
Yeah, it seems there are some, but you can speak or. You want to speak? I see that you can unmute it. Do you have a question? Okay.
Я ничего не слышу, если кто-то говорит. Я ничего не слышу, можно погромче?
Денис, почему не слышно? Андрей, не слышно?
Саша, тебя слышу.
Сейчас слышно? А мы там слышим?
Саша, тебя слышу.
Меня слышно, да?
Да.
Вот, да, есть вопрос. Андрей, so is there a differential version of this particular model which you talked about the sequence operators? Does it have some analog, neutral analog or differential?
Миша, I'm sorry, I don't hear. Можно по-русски погромче?
Ну, вопрос про дифференциальный аналог этого последнего примера, о котором ты говорил. У него есть? Is there a differential version of analog of this example?
Of course, there is a differential version of this last example. And also, coefficient of matrix partial differential operators are rational functions, similar to this difference case.
Any other questions? Well, let's thank the speaker again.
Okay, thank you very much. We have now a 15 minutes break. The next talk is as scheduled in 4:20.
Евгений, если хотите, можем сразу начать вашу уже презентацию, просто ее поставить на экран. Либо можем это сделать чуть попозже.
Нет, давайте попробуем. Сейчас. Так видно?
Отлично.
Нормально?
Видно. Отлично видно.
Ну все, тогда отлично.
Тогда через 11 минут начнем.
Через 11 минут. Хорошо. Ага.
Evgeny, do you hear us?
Can you hear me?
Yes, yes.
Yeah, all right. Yeah.
Yeah.
Well, the next talk, the next speaker is Evgeny Ferapontov. He will speak about second order PDEs in three dimensions with Einstein-Weil conformal structure.
Thank you very much. It's an honor to speak at this conference. So in my talk, I will give a brief review of our old and relatively recent results on dispersionless Hirota type equations in 3D and the extension to arbitrary second order PDEs in 3D based on the concept of Einstein-Weil geometry. I will define all these concepts in my talk. So over my career, I had the privilege for nearly 40 years to discuss research with Boris Anatольевич, first as a student of Moscow University, then participant of the seminar on geometry and mathematical physics, then as a visitor at CISA. And Boris Anatольевич has always been extremely generous with his time, was always prepared to listen, to give his advice. In particular, this project has been discussed with him on several occasions. So unfortunately, I was not able to report our final results. So I will do this now. All right, how do I go down? All right, so this is the plan of my talk. I will start with a brief review of integrable Hirota type equations in 3D. Then I will introduce Einstein-Weil geometry in 3 dimensions. And then I will discuss our recent results on general second order PDEs in 3 dimensions with characteristic conformal structure with Einstein-Weil property. It turns out that there are quite a few statements one can make in the general case. All right, so let's start with dispersionless Hirota type equations. So these are just second order PDEs of this form. Here, U is a function of x1, x2, x3, 3 independent variables. And I have a single relation connecting second order partial derivatives of the function. So you see independent variables, x is u itself, and first order derivatives of u do not enter this equation. Only second order partial derivatives. These are called dispersionless Hirota type equations. Right, well-known examples are the following. I list them here. So this is the so-called dispersionless Kadomtsev-Petriashvili DKP equation. This is Boyer-Finley or dispersionless Toda equation. And this is what is known as dispersionless Hirota equation. So these PDEs typically arise from integrable to the 3-dimensional integrable hierarchies in the dispersionless limit. In this limit, higher floors of the hierarchy become commuting second order PDEs of this type. Okay, so let me show you, so far these examples are in elementary functions, but in fact the generic integrable Hirota equation is quite a non-trivial object. Let me show you one example which shows that the answer, we shouldn't expect an elementary answer. So let's consider PDEs of this particular form. Here phi is some function of uxx. Right, so we impose, yeah, by the way, I forgot to say in what sense I understand integrability. Right, I don't want to give a precise definition, but intuitively, we say that a PDE in multi-dimensions is integrable in dispersionless sense if it possesses infinitely many dispersionless analogs of multi-soliton solutions. Let me not make this precise, but this definition imposes constraints on the equation, and we can obtain classification results. So you see in 3 dimensions, the standard approach based on high symmetries or high conservation laws doesn't work, because all these objects become non-local and hard to compute. However, this method, I call it a method of hydrodynamic reductions, which postulates the existence of dispersionless analogs of multi-soliton solutions. So this method is efficient and allows to obtain classification results. So anyway, if you take PDEs of this form with function phi at this stage unknown and apply the integrability test, you get a third order ODE, this third order ODE for phi, which is known as the Chazy equation. And this example is due to Maxime Pavlov. So the general solution to this equation, generic solution, is a modular form. Strictly speaking, it's a quasi-modular form. It's the Eisenstein series of weight 2, which has this expansion. Right? So you see, even in this simple case, the answer is quite non-trivial. The coefficient of this PDE must be a modular form. And this was one of the first examples where modular forms occurred in the coefficients rather than in the solutions to integrable PDEs. So the general answer here is quite non-trivial. I will show what is the generic integrable Hirota equation. Okay, but I'll formulate it on the second, in one of the next slides. So let me summarize what is known, what was known about integrable Hirota type equations in 3 dimensions. First of all, this class of PDEs is invariant under the equivalence group SP6R, which acts on the equations via linear symplectic transformations. So you take the Hessian matrix of the function U. So U is the Hessian matrix of second order partial derivatives. Since U is a function of 3 variables, so this Hessian matrix will be a symmetric 3 by 3 matrix. And it turns out that standard linear fractional transformations of this kind, they preserve the class of Hirota type equations, and they preserve the integrability. So therefore, it's natural to classify integrable equations modulo these equivalence transformations. So then we proved, so it was in quite some time ago, that the parameter space of integrable Hirota equations is 21-dimensional. This was done as follows. So we represented Hirota type equation in evolutionary form, say UTT equals a function of the remaining 5 second order variables. And for this function, we obtained derived integrability conditions. This was a finite type PDE system, which was an involution. And once you have an involutive PDE system, you can calculate the parameter space of the dimension of the parameter space of solutions. And it turns out to be 21-dimensional. Furthermore, we proved that the action of this equivalence group SP6R on the parameter space is locally free. So in other words, for a generic equation, the stabilizer is trivial. To be precise, it is discrete. It's not trivial, it is discrete. But there is no continuous symmetry preserving a generic integrable Hirota equation. Note that dimension of SP6R is also 21, so it equals the dimension of the parameter space of integrable equations. So what does this mean? This means that there is an open orbit in the parameter space of integrable Hirota equations. In fact, there is a unique Hirota master equation, which doesn't contain any parameters, any moduli. So there is a unique Hirota master equation which generates this open orbit. And all other equations, for instance, I showed you DKP, Borg-Finley, all these examples in rational functions are kind of degenerations of this generic solution, right? Non-trivial degenerations. And so the question remains, so what is this master equation? So it should be somehow related to modular forms, because even in the simple example on the previous slide, the coefficients are quasi-modular forms, right? This was, and this is exactly the question I discussed with Boris Anatольevich on several occasions. He encouraged me to continue it, to give me some advice. So, and eventually we found this generic Hirota master equation. It's given by the following formula. So here theta m is a genus 3 theta constant. So Andrei Mironov introduced theta functions in his talk. So theta constant is when you set z equals 0 in the theta function. So you view theta function as a function of the modular variables of the symmetric matrix. So a function on the Ziegler upper half space. Right, and z is set equal, abelian variable disappears, it's set equal to 0. So let us substitute as the argument of the theta constant, let us substitute the Hessian matrix of the function u multiplied by I. This is just to make the answer real valued, right? To make the equation real valued. Then this equation, theta m applied to evaluated at a Hessian matrix equals 0, is so it's just a PD. You can view it as a PD for the function u, because tau is expressed in terms of second order partial derivatives of u. So this equation is a PD for the function u. So I claim that this is the generic integrable Hirota equation. Everything else is sort of its limit, right? And this was obtained in our joint paper with Fabien Cléry. And the proof of this result, unfortunately, it's indirect. We couldn't prove directly that this equation, that this formula satisfies the integrability conditions. So there are some complications in this direction. And our proof is indirect, is based on the Adesky-Sokolov construction. So there is a paper by Adesky and Sokolov parameterizing broad classes of dispersionless integrable systems in terms of generalized hypergeometric functions. And so if you apply their construction, then in the particular case, this is the result you get, all right, if you interpret it appropriately. All right, so this is the result you get. So the generic Hirota master equation is a hyperelliptic equation of hyperelliptic divisor. Because this equation, when theta constants with even characteristics equal 0, these equations define the hyperelliptic divisor in genus 3, all right? Here, M is any even theta characteristic. All right. So then it was, okay, now I want to relate the above result to Einstein-Wald geometry. Einstein-Wald geometry will be defined in the next slide. Now I will formulate the statement. So suppose we are given a Hirota equation of this form. Second order PD depending on second order partial derivatives only, right? Let's define its principal symbol, or in the PD theory, it's called also the characteristic variety. So it's just this expression, df by du xixj pi pj. Principal symbol of a, or it's called symbol of a formal linearization. So it's a quadratic form and the variables pi pj. Usually it's written in this form. Pi's are treated as a covector components. So then these coefficients df by du xixj, these partial derivatives are treated as components of a metric with upper indices, right? Metric with upper indices. So we have this is called the principal symbol, right? So let us calculate the corresponding conformal structure. So we have to invert this matrix. So characteristic conformal structure is this object. Here x is our independent variables, x1, x2, x3, and this matrix Gij with low indices is the inverse of this Gij with upper indices, just the inverse matrix. So this is called the characteristic conformal structure. This is also a well-known object, not necessarily in the context of integrable PDEs, just in the PD theory. This is a standard object for linear and nonlinear PDEs. Okay, so this is easy to compute. So once you have your equation, you directly compute this object, right, by just calculating these partial derivatives. Let us introduce the following one form. So using these coefficients Gij, we now introduce one form of covector omega with three components, omega 1, omega 2, omega 3, defined by this formula, defined by this explicit formula. Here, this d is total derivative in the variable x, in the independent variable xk, dxk, total derivative in xk. Right, again, so this is straightforward to compute. Once you know your PDE, you directly compute this covector omega. So, and then we prove the following result with Boris Kruglikov. We prove that integrability of dispersionless Hirota equations, of these equations, in terms of the method of hydrodynamic reductions, in terms of these dispersionless multi-soliton solutions, is equivalent to the Einstein-Wald property of this pair, G omega. Okay, I will explain now what Einstein-Wald geometry is. So to summarize, you can define integrability of Hirota type equations based on the method of hydrodynamic reductions. And equivalently, you can define integrability of these equations by requiring that the characteristic conformal structure G and the corresponding covector omega satisfy Einstein-Wald property on every solution of the equation, right? So modulo the equation on every solution of the equation. So now I will define Einstein-Wald geometry. And it turns out that integrability by hydrodynamic reductions doesn't generalize naturally to arbitrary second-order PDEs. Well, this result, Einstein-Wald geometry approach, it generalizes to arbitrary PDEs, which are allowed to depend on all jet variables. All right, so Einstein-Wald geometry. What is Einstein-Wald geometry? This is a triple symmetric connection D, conformal structure G, and covector omega. G and omega are exactly the ones from the previous slide. I haven't explained yet what this D is. In fact, this connection, symmetric connection D, it's not the Levi-Civita connection of the metric, but it's defined by G and omega. It's called the Wald connection, symmetric Wald connection. So what are the Einstein-Wald equations for this triple? All right, first of all, you have these Wald equations. These equations, this set of equations shows that covariant derivative of the metric is proportional to the metric. So if you put here on the right-hand side, if you put here 0, right, dk Gij equals 0, then you get Levi-Civita connection, right? Connection, symmetric connection in which the metric is covariantly constant. But here we put this omega k Gij. This is called the Wald connection. To define a Wald connection, you need G and omega. So this pair defines your connection. So in a sense, yeah, this is a secondary object, right? G and omega define D uniquely from the first set of equations, right? And the second set of equations says that the Ricci tensor of this connection D, Ricci tensor of this connection is proportional to the metric. Lambda is some function, right? Coefficient of proportionality is not a constant in general. All right, so this round brackets denote symmetrization, you see, because if you take a Ricci tensor of a Levi-Civita connection, it's always symmetric, it's a well-known fact. But for a generic connection, affine connection, Ricci tensor doesn't need to be symmetric. So this is Einstein equation. This together, these two equations are said to define Einstein-Weyl geometry. These are Weyl equations, these are Einstein equations. All right. So this has been introduced by Elie Cartan around 1940s. In the it was not related to general relativity. It was introduced in the context of his geometric theory of ordinary differential equations, in particular third-order ODEs with special properties. Okay, this is a conformal theory. Why it is called conformal? It turns out that these equations will be identically satisfied if you change from G to lambda G, where lambda is some function, and omega goes to omega plus d log lambda. So it turns out that these equations will be identically satisfied. Therefore, this theory is conformal. Metric, it's more natural to speak about a conformal structure rather than a metric. G is a conformal structure. So, and Cartan proved the following result. Kind of equivalent geometric interpretation of these equations, right? Geometric interpretation of these equations. He proved that these equations are satisfied if and only there exists a two-parameter family of surfaces which are totally geodesic with respect to this connection and null with respect to the metric. Okay, now I'm in 3 dimensions, by the way. And I forgot to mention that Einstein-Weyl geometry makes sense in any dimension, right? Any dimension. You can define this. These equations make sense in any dimension. But they're only interesting in dimension 3, where it turns out that these equations form an integrable system. Dispersionless integrable system. Einstein-Weyl equations are integrable. The result of Cartan is the following. So in 3 dimensions, this triple satisfies these equations, triple dg omega, if and only if there exists a two-parametric family of surfaces, totally geodesic with respect to the connection, null with respect to the metric. So let me briefly explain this terminology, although I won't really need it later, but okay, to be self-contained. What does it mean that a surface is totally geodesic with respect to the connection? It means that if you start at a point on the surface and take a tangential direction to the surface at this point, okay, and then you construct a geodesic in 3D, in 3 space, in the ambient space, which starts on the surface in the tangential direction to the surface, right? Since we have connection in this ambient 3-dimensional space, it makes sense to speak of geodesics, right? So, and a surface is said to be totally geodesic if geodesics in 3D starting on it in tangential direction stay on it forever. They do not escape. Okay, let me give you a simple example. Let's take a sphere in 3 space and take its north pole and take a tangential direction to the north pole on the sphere. Then geodesic through the north pole in this direction will be a straight line in 3 space. You see, straight line doesn't belong to the sphere. This means sphere in 3 space is not totally geodesic. Geodesic escapes from it. But if you take a plane in 3 space, then if you start in tangential direction to a plane, you remain on this plane. Planes are totally geodesic. This is a trivial example, but this explains what totally geodesic means. Now, what does it mean that the surface is null with respect to the metric? So we have a metric in these 3 dimensions. We have a surface. We can restrict the metric to the surface. In general, in elementary differential geometry, this is called the first fundamental form. And this restriction is non-degenerate because G is Riemannian. By the way, also I forgot to mention that G is usually Lorentzian in this context. But there are surfaces for which the restriction of G to the surface is degenerate. All right, so it's not a Riemannian metric, it's degenerate. And such surfaces are called null. Okay, this is Cartan's result. He proved that Einstein-Wald conditions are equivalent to the existence of totally geodesic null surfaces. I will show you on the next slide that these conditions can be, in fact, they mean that Einstein-Wald equations possess a Lux pair. But they're stated in geometric terms, so you can't see the Lux pair. It's not immediately, this Lux pair is not immediately visible. It turns out that these totally geodesic null surfaces, they somehow contain a Lux pair now. All right, and finally it was proved by Hitchin that 3D Einstein-Wald equations are integrable by the twistor construction. Right, let me make all this very precise on the next slide. I will give you a direct parameterization of Einstein-Wald spaces in terms of a certain PD system, right, where everything becomes very precise. Let's consider the so-called Monakov-Santini system. So this is a pair of second-order PDEs shown here. So U of x yt and V of x yt are two arbitrary functions, and they are restricted to satisfy these two PDEs. It was observed by Maciej Dunajski that if you introduce a conformal structure by this formula and covector omega by this formula, then this pair G and omega satisfy Einstein-Wald equations if U and V satisfy this Monakov-Santini system, right? So G omega satisfy Einstein-Wald equations if the Monakov-Santini system is satisfied. You see, U and V, they appear here in the coefficients, U and V from this system. And then we proved later that all Einstein-Wald structures locally rise in this way, right? Locally, every Einstein-Wald structure can be written in this form. It was known that this system possesses a Lux pair. Dispersionless Lux pairs are a bit different to the conventional Lux pairs. They consist of two commuting vector fields. So let's take X and Y, two commuting vector fields. So two vector fields depending on auxiliary variable lambda. So you can check that the commutativity of these vector fields is equivalent to these two equations. So these equations are satisfied if and only if these vector fields commute identically in lambda. So these vector fields live in the extended, and this means, by the way, twistor integrability. What does it mean that Einstein-Wald structures are integrable by the twistor construction? More or less, it means this property, that there are commuting vector fields which produce the system. All right, let's view this vector. These vector fields are naturally defined in this four-dimensional space, x, y, t, lambda. So, okay, and they commute. Therefore, they have integral surfaces. They define a two-dimensional integrable distribution in four-dimensional space. So we have integral surfaces of this distribution. Let's project them down to the xyt space by just ignoring the coordinate lambda, forgetting lambda. Let's project them down to the xyt space. It turns out that then we obtain Cartan's two-parametric family of totally geodesic surfaces. All right, so Cartan's totally geodesic surfaces more or less encapsulate the Lux pair. All right. Now, what can we say? Now I'm coming to the second half of my talk. What can we say? But it will be shorter. What can we say about general second-order PDEs in 3D? Just arbitrary second-order PDEs. So whose conformal structure is Einstein value on every solution. So you can construct characteristic conformal structure for any PDE, not necessarily Hirota type. So you are allowing now dependence on first order jet variables, all these first order jet variables, right? And okay, we require that this conformal structure satisfies Einstein value equations for suitable covector omega, which is yet undefined, right? So our first result is that this covector omega, in fact, can be reconstructed in terms of the equation uniquely. It's given by this formula where this bit is the same formula as for Hirota equations, when you do not have this low order dependence, right? Only second order derivatives. This is the same formula as before, but you need correction terms, right? Which are not zero in general, and they're quite complicated. So this is kind of, we have the existence result that this omega, if G omega satisfies Einstein-Wall conditions, then omega can be reconstructed uniquely. And this provides an efficient integrability test. So you have a PDE, so a class of PDEs of this form, right? So you construct its Einstein-Wall characteristic conformal structure, you construct this covector, and then you impose Einstein-Wall conditions. And this is an efficient test. You can verify it by computer. And our second result, I can't call it a result, it's a conjecture, sorry. It's a conjecture. We call it rigidity conjecture, which says the following. Suppose we have a generic second order PDE. What does it mean, generic? It means, not, for instance, not Monge-Ampere PDE. So in other words, its dependence on higher order derivatives should be sufficiently non-trivial, not like for Monge-Ampere equations, right? Then it turns out that if such PDE satisfies Einstein-Wall equations, then all dependence on this lower order jet variables can be eliminated by a contact transformation. Right? This was unexpected for us. We were expecting to get some kind of deformations of this theta functional formula for Hirota equations, for generic Hirota equations, but it turns out that it's not the case, unfortunately, or fortunately. So all dependence on low order jet variables can be eliminated. But this is only true if the equation is not Monge-Ampere. If it is Monge-Ampere or quasi-linear, this is no longer true. I will show you, I have 2 more slides. I will show you one classification result, and then I will show you one example confirming the rigidity conjecture, which is entirely open. Okay, so as an example, let me show you the classification of quasi-linear wave equations, right? UTT is some coefficient times UXY, right? Quasi-linear wave type equations. No problem, you can replace this by UXX plus UYY. Just in this case, the answer is a bit nicer. So it's no problem to write down the characteristic conformal structure. It's this, it's just this. F is the same function as here. At this stage, unknown function of all these variables. And then we can calculate the covector omega. It's given by this explicit formula. dt is total derivative with respect to t, and phi is some extra correction term which can also be expressed in terms of f uniquely, right? But the expression is much longer, so I'm not writing it down. Then you impose for this pair, you impose Einstein-Wall conditions. You require that they hold on every solution of this equation. Einstein-Wall conditions hold on every solution of this equation. And then you end up with certain differential constraints for this coefficient, and they are straightforward to solve, and we get canonical forms. Canonical forms for instance, when f is e to the ut, it's a version of the Bohr-Finley or dispersionless-Toda equation in this last case. And these are certain generalizations. When f is this generic thing, it's called something like singular manifold dispersionless-Toda, something like this. Right, and let me finally show you one example of a rigidity result. So remember that equations of this form are integrable if phi satisfies the Chassis equation, third order nonlinear ODE, and its generic solution is the Eisenstein series E2. Right, so we tried to generalize this ansatz, and instead of phi of uxx, we allowed some function f of x, ux, uxx. Just something to start with, right? And we imposed the integrability conditions, these Einstein-Wald conditions on every solution. We got a PDE system for f. In fact, we were hoping to get a deformation of this Eisenstein series in these extra variables, right? But what came out is a certain explicit answer which involves this Eisenstein series and some arbitrary functions. And then we realized that this answer simply means that there is a contact transformation which brings equation of this form to this form. In other words, every deformation of this kind, of the type 2, is trivial, right? It's an artifact of a contact transformation. And we have many more examples of this kind where, okay, it's clear that every deformation is trivial, although the jets can be eliminated. But okay, this is not proved at the moment. I think I will stop here. Thank you very much.
Thank you very much. Any questions?
There is a comment in the chat, I think.
Evgeny, there is a question in chat.
In chat, well, let me see. Physics of heavenly in 4 dimensions. All right, thank you very much. I'll have a look. Thank you.
Well, any other questions or comments? Well, if not, let's thank the speaker again. And now we have a coffee break.
Thank you.
Можно вопрос? Меня больше.
Евгений?
Sorry, I have to stop sharing or what?
No, we already stopped it for you.
It's all right, yeah? Okay.
Yeah, I think there was a question to you from Mikhail Feikin.
Жень, may I ask you one thing?
Миша, да, рад видеть.
Я тоже, да. Спасибо за доклад. Вот тебя видеть тоже. Just want to ask, so in the beginning, when you were considering this dispersionless...
Да ты можешь, наверное, по-русски можешь.
Давай, смотри, хорошо. Значит, когда была первая часть, там бездисперсионные уравнения с двумя переменными, ты сказал, что ну вот есть это общее мастер решение, 21-мерное пространство. Я не совсем понял. То есть это, ну, как можно, ну, верно ли, как можно понять, что в пределе получаются все там в некотором смысле интегрируемые уравнения?
Ну вот смотри, Миш.
Это верно, что в пределе получаются все?
Да,
все?
Верно. Ну потому что это открытая орбита.
Ну, может, изолированно есть какое-то еще?
Нет, нету. Это там как бы оно, это такая открытая орбита, и ко всему можно приблизиться. Я только не знаю, как это делать.
А как это можно доказать, что можно?
Это как бы алгебраическое многообразие. Вот можно доказать так, что вот пространство этих интегрируемых уравнений – это алгебраическое многообразие. На нем действует алгебраическая группа. И есть открытая орбита. И как бы она плотна. Вот. И ко всему можно приблизиться. Но как это сделать, я не знаю. Какие-то частные вырождения строились, но общего, вот как к ДКП, например, как выродить в ДКП, я не знаю. Это, наверное, сложно. И вообще, вот как бы вопрос, открытая задача – это описание всех сингулярных орбит. Вот всех орбит не общего положения. Общая открытая орбита одна. Вот, дальше можно доказать, что дальше там где-то лежит линейное уравнение. У него самая маленькая орбита, потому что у него стабилизатор большой. После этого идет ДКП. У него побольше орбита. Вот, но тоже большой стабилизатор. А как вот описать все вот такие вот орбиты не общего положения? Это, ну вот как, мне очень интересно, но я не знаю как.
Размерности их известны, этих орбит всех?
Они, по-моему, начиная... Да, я думаю, там нету гэпов даже, они просто идут там подряд.
То есть неизвестно количество, например, в каждой размерности?
Да, количество неизвестно, и там могут быть параметры. Это, знаешь, как вот напоминает торические многообразия. Вот у торического многообразия у него есть открытая орбита, Тор, да, и там к нему примыкает много орбит маленькой размерности. И здесь то же самое, только здесь вместо Тора вот СП, СП6. Вот. Ну, в общем, да, там я не знаю, как делать.
Понятно, спасибо большое.
Ладно, Миш, свяжемся.
Давай, да. Пока. Спасибо.
Спасибо. Ты когда назад, кстати?
Я либо в воскресенье, либо там через несколько дней. У нас следующей неделе в любом случае, я думаю.
Созвонимся, у меня будут вопросы, ладно.
Я на самом деле тоже тебе хотел написать. Я тебе написал уже драфт, но еще не отправил.
Хорошо. Хорошо.
Ладно,
Счастливо.
Свяжемся.
Да.
Пока.
Удачи.
Давай.
сказать?
Он уже...
Он еще здесь, может быть. То есть можем спросить здесь или еще.
Телефон тут?
Ну, да, он взял в списке, но может быть его здесь нет. Но надеюсь, что может быть он откликнется.
Ну, смотрите, я думаю, что
Hi, Professor Dragovich.
Здравствуйте, Денис.
Здравствуйте, Владимир.
Как у вас тут?
Взаимно. Значит, вам, наверное, нужно дать возможность показать экран, правильно?
Да, это было бы как-то
Вот,
кстати.
значит, у вас есть такая... Сейчас, значит, права вам на это дело выданы, и вы можете спокойно это сделать, если вы хотите, чтобы мы проверили, что все работает.
Давайте попробуем. Давайте попробуем.
Потрясающе. Все видно, вашу мышку видно, если вам это нужно.
Да, это хорошо. Надо только мне как-то убрать вот эту полосу, где имена участников, потому что она закрывает. Ну, хорошо.
Вы можете просто на крестик, значит, там есть стрелочка вниз, там должно быть close.
А я прошу прощения, но в общей картинке ничего не закрывается. То есть у нас...
Да, я понял, но просто...
Ага, привет,
просто
Владимир.
мне закрывает немножко. Ладно, я сообразил. Мне пока все удобно. Все хорошо. Спасибо. Сейчас посмотрим, работает ли это. Да, двигается так, что...
Ну, тогда через примерно 9 минут мы, видимо, начинаем.
Да. Давайте. Я значит, оставляю все так, да?
Да, конечно. Никакой проблемы нет. Угу.
Только мне надо, как мне это выключить, звук собственный, да? В данный момент. Ну, ладно, это не удается. Да, понял.
Да, у нас сегодня сессия по Zoom, поэтому в аудитории не слишком много людей присутствует.
Vladimir, nice to see you.
Yes, I also am very glad to see you all.
We'll start in 1 minute. Maybe.
Okay.
Well, the last talk today is by Vladimir Dragovich. He will speak about Chebyshev dynamics, isoharmonic deformations, and constrained Schlesinger systems.
Thank you very much. First, I would like to thank the organizers for all the efforts to put this very important event dedicated to the memory of Boris Anatольевич Dubrovin in these unstable times. I was sincerely planning to join you in person in Moscow. However, due to this situation, apparently I was not able to collect all formal approvals, and I have to participate now online. Thank you for providing me also this opportunity. So my talk is based on joint work with Vasilisa Shamchenko and also on some work in progress. Somehow, let me just see. Yes. So of course, this talk is dedicated to Boris Anatольевich, the teacher, and both there are many common fundamental words in Serbian and Russian, and one of them, one of the most important, is učitelj. So this is dedicated to посвящается моему учителю. We met for the last time in Trieste on January 22nd, and then we briefly discussed some of the questions which I'm going to mention today. As a reflection on that meeting, I started to understand better these famous lines from Hemingway. His eyes, and they were the same color as the sea, and were cheerful and undefeated. So the talk is based on this series of papers, and also, as I said, on some current work in progress with Vasilisa Shamchenko, which I hope that we are going to put on archive very soon. So let's mention about Chebyshev polynomials, very well-known object, which appears in various fields of mathematics, as you all know, and applications. And here are some of properties. So we here see Chebyshev polynomials on the interval -1, 1, and we see them of degree 6 and degree 9 as examples. And we know that Chebyshev polynomials satisfy several remarkable properties. To mention a few, they satisfy functional polynomial Pell equation, and they also satisfy this min-max condition on this interval -1, 1. And then one can ask a question: what if we want to deform this interval -1, 1 and study either this min-max problem or the solutions of Pell equation on deformed intervals? And the answer is trivial. We can apply a fine transformation on this one interval from -1, 1 to another interval, and this affine transformation will transform interval into interval and min-max polynomial to another min-max polynomial, and the solution of Pell equation into a solution of Pell equation. So in a sense, for what we are going to study today, the case of one interval is trivial. Let me also mention that this year, 2021, is also a jubilee, bicentennial of birth of one of the founding fathers of Russian mathematics and one of the leading mathematicians of the 19th century, Pafnuty Chebyshev. And as we can see, Russia issued a stamp related to this event. And actually, in some sense, I will not have time to explain, but this mechanism you see in the background is to some extent related to what I'm going to talk today. But now, let us go to the situation of two intervals. And Chebyshev, as a great mathematician, he had important students as well, and Zolotaryov was one of them. So he studied following the spirit of his teacher.
May I ask you a question?
Yes.
Sorry, hello. Hello.
Hello, hello.
About Achille, because there is what you are telling about, it is related with that. Because I remember in the classical book of Achille about Chebyshev polynomials, we considered union of two intervals generalization. So you do you do almost the same thing that was done in Achille's book, or no?
I will comment on that. It will come.
I'm sorry.
So I will comment on that. It will come in one of next slides, if you don't mind. So I will explain this. This is an excellent question, and this is directly related to work of Achiezer, and I will explain this in just a few slides. So so now we have suppose we have two intervals, and we can ask the same question: find monic polynomial of degree n, minimizing the uniform norm at the union of these two intervals. And then if you know this solution as Pn hat and this norm as Ln, then what is going to happen? Is this solution going to satisfy Pell's equation? And the answer in general is no, because the answer is no and yes at the same time. So maybe no for these given two intervals, but if we extend a little bit these two intervals, we can get a bigger two intervals, and then for maximal such, they will satisfy Pell's equation with this polynomial and these endpoints. So we see that there is a non-trivial difference between a case of one interval and two intervals, meaning that not any two intervals can serve as endpoints of the solutions of Pell's equation. However, we can extend them and get a maximal subset where these new intervals are going to be solutions of Pell's equation. So here is example of Zolotaryov polynomial on two intervals, lambda 1, lambda 2, and lambda 3, lambda 4. In such a polynomial has a gap critical point, this gamma hat, on this gap interval, lambda 2, lambda 3. So lambda 2, lambda 3 is not a part of our set where we do this min-max construction. This is lambda 1, lambda 2, union lambda 3, lambda 4. So the question is now, what if we try to deform this? What if we try to deform this picture, but under the condition that this configuration remains? In a sense, how can we deform lambda 1, lambda 2, lambda 3, lambda 4 in a way that the solution of Pell's equation, this polynomial which you see the graph here, transforms again into a polynomial which is solution of Pell's equation. So again, using this affine transformation, we can, for one interval, for example, this lambda 1, lambda 2, we can keep it fixed. So we can use this affine transformation, which we can use as a sort of a trivial gauge. We can keep one interval fixed, but then the question is, suppose we fix one interval, then if we then move lambda 3, for example, how lambda 4 should evolve, or how gamma hat should evolve, in order that this deformed picture is still a picture of a graph of a polynomial, of a Zolotaryov polynomial, of a minimax polynomial satisfying Pell's equation on this deformed set of two intervals. Apparently, this is related to Penlevé equations. This is related to Penlevé equations, more precisely to Penlevé-6 equations. And here I'm providing you the definition of Penlevé-6 equations, which depend on 4 parameters, alpha, beta, gamma, delta. And for our story today, 2 sets of parameters are going to be important. But of course, this Penlevé-6 equation in the form which is written here is very difficult to follow and difficult to remember. Yuri Ivanovich Manin, in his study of Penlevé equations at the end of 90s, came to this beautiful form representing Penlevé-6 equation through elliptic functions. And you see it's much more compact. It depends on 4 parameters, which can be expressed through 4 parameters, original 4 parameters in a very simple, with a very simple substitute. And as one can learn from one of the footnotes of one of these papers of Yuri Ivanovich, somebody paid attention to Yuri Ivanovich that actually that form, this beautiful compact form in elliptic form, Penlevé-6 equation, was known to Penlevé himself in 1906. So from this form, we can do one simple exercise, and we can put all this alpha naught, alpha 1, alpha 2, alpha 3 equals 0, which in our original parameters alpha, beta, gamma, and delta goes to 0, 0, 0, 1 half. And we are recognizing, transforming to the original equation, we recognize so-called Picard equation. And with Picard equation, it goes a Picard solution, which gives general solution of that equation in terms of a little bit modified Weierstrass P function. But what is important here is, apart from this historic moment, the Picard equation and Picard solution appeared something like more than 10 years before Penlevé-6 equations in general. You see that this Picard solution, you can see as sort of looking at this formula for z naught of x, you see that x is a variable branching point of this elliptic curve, and then tau of x is a parameter describing, if you want, a Jacobian of this elliptic curve, which is isomorphic to this elliptic curve. And this also depends on x. But this C1 hat and C2 hat are constant. They don't depend on x. And this idea is going to be a little bit translated in different languages, is going to be one of the leading ideas of what I'm going to talk about. So one important ingredient comes from Okamoto transformations from 80s, and one particular and probably the most non-trivial one together with Vasilisa Shamcheko, we rewrote in this form, which is for us useful. So this is a Komodo transformation connecting Penlevé 6, 0, 0, 0, 1/2 with Penlevé 6, 1, 8, minus 1, 8, 1, 8, and 3, 8. And you see this formula y of x. This is general solution of Penlevé 6 of 1, 8, minus 1, 8, 1, 8, 3, 8, connecting with y naught, which is solution of Penlevé 6, 0, 0, 0, 1/2.
Can I ask you a question? I'm sorry, because my question is very pragmatic. Can we understand solutions of Picard equations in terms of Chebyshev polynomials? Because I'm sorry, it's a very stupid question because I asked you a question.
I'm coming to that.
Sorry.
Coming to you. You're asking great questions, but we are setting a scene. We are setting a scene and the background, and then we will try to formulate some of these answers. So we will also need this theorem, our theorem of a couple of years ago. So if x varies and C1 and C2 stay fixed, as it was in Picard's solution, then y of x, this is the general solution of Penlevé 6, 1, 8, minus 1, 8, 1, 8, and 3, 8, is the zero of one certain differential of third kind, and at the same time is the Okamoto transformation of y naught according to the formula above. So what I want to say is we found a construction, invariant algebraic geometric construction on families of elliptic curves, which give us general solution of this Penlevé 6, 1, 8, minus 1, 8, 1, 8, 3, 8 as position of a zero of some differential. Now, going slowly toward the answer of one of these questions. So now, suppose that we have these two intervals. We have these two intervals, lambda 1, lambda 2, lambda 3, lambda 4. It is natural to assign to them the elliptic curve as in Formula 1. So this is a mu square equal this polynomial of 4 degree in lambda. And then we assume that Pell equation is satisfied. This is this equation 2. Having this equation 2 then satisfied, we are getting a particular very important meromorphic function, this P of n of lambda and mu, which is Pn of lambda plus mu Qn minus 2 of lambda as a function of this elliptic curve. And then following a beautiful book of Bogatyrev of external polynomials and Riemann surfaces, although we did this at that point without knowing exactly these results in this book, but they are explained there, one can construct the differential, which is logarithmic derivative of this function Pn. And the zero of this differential in this setting is exactly this gamma hat, the gap critical point of Zlotaryov polynomial. As a consequence, we are getting that this curve, elliptic curve, given by equation 1, allows the solutions of Pell equation exactly if the infinity is the point of order n. But now, in order to fit this to our construction of solutions of Penlevé 6 of 1, 8, minus 1, 8, 3, 8, and 1, 8, we need to transform our curve L of lambda into a curve of L, which is going to be, again, of course, elliptic curve, but in this time given by equation 4, which is v squared y times y minus 1, y minus x, where now the fourth branch point goes to infinity, and infinity, which was before point of order n, goes now to a fine part to some point y naught, which is going to be point, or I here have it as the point q naught, which will be the point of order n of this new curve L. So the point is that with Pell equation, we are getting one marked point of a fixed order as point on this given elliptic curve, and then by varying these elliptic curves while satisfying Pell equation, we're getting a sort of a section of points on this fiber fiber bundle with fibers as elliptic curves of finite order, finite fixed order. And now we can put these two things together and applying this Mobius transformation, which transforms one curve into another, we get that the function y of x, which is given here, in terms of this gamma hat and endpoints of these intervals and y naught, is going to be the zero of differential omega, and means that it's going to be a solution of Penlever 6 equation 1,8 minus 1,8, 1,8, 3/8. And here are exact formulas for y naught and the argument x in terms of lambdas and in terms of lambdas. But now we can also redo the calculation, and we can see that if we are deforming Zolotaryov polynomial in a way, if we are deforming intervals in a way that Pell's equation is satisfied all the time, in the sense that Zolotaryov polynomials deform into themselves, into Zolotaryov polynomials, then critical gap point gamma hat is going to evolve according to this formula: y lambda 4 minus y naught lambda 1, y minus y naught, meaning that we are getting that this gap point is deforming along the law in which participate two solutions of two Penlever 6 equations connected via Okamoto transformation. But now I'm coming to, I think, more closely to one of the questions I got in the audience on early stage. Indeed, so after Zolotaryov, it was Achiezer who studied intensively these polynomials, and he got a parametrization in elliptic functions of intervals, which can be supports of Zolotaryov polynomials. And there are several such parametrizations depending which endpoint you fix here. If you fix first left endpoint is -1 and the second right point is 1, here are these unions of intervals, and here are explicit formulas obtained by Achiezer in terms of elliptic functions. And in particular, there is also a formula which is very big, and I didn't put it, but there is also a formula in terms of elliptic functions of the second highest coefficient, which I will denote by minus n tau 1 and m. This is again the result of Achiezer. So from there, we are getting that this unique critical point can be expressed in this formula. In this formula through endpoints of intervals and the second coefficient, which are all expressed explicitly in terms of elliptic functions. So now we can use this in opposite way. So first we use Penlever equations to describe Zolotaryov polynomial dynamics. Now we are going to use information from Zolotaryov polynomials, this Achiezer parametrization, to deduce explicit solutions of Penlever equations. So this is my next slide. So now using these formulas, we are getting accountably many explicit solutions of Penlever 6, 1,8 minus 1,8, 3/8 and 1,8 by plugging this formula from Achiezer. So this is one result in opposite direction, where now knowing information about Zolotaryov polynomials, which came from Achiezer, we are getting an explicit solution of Penlever 6 equation. But that was with two intervals which were supports of Zolotaryov polynomial. But now, as I said, most of unions of two intervals don't qualify for that. They don't qualify for that. So can we do something similar with unions of two intervals not having Zolotaryov polynomials in the background? So this is the next question I'm going to try to answer. In order to do this, we're going to look into, first, we're going to translate our problem into the language of harmonic analysis. And the second, we are going to use yet another harmonic map. So we can, from complement of two intervals into annular domains. And then we're going to see what is going on in this new screen in the new language. So new language is language of harmonic analysis, and the new screen is going to be a screen of annular domains. So here is just a brief account of basic notions from harmonic analysis. Which I'm going to use, but I'm not going to enter into this. The most important here is that, of course, green function can serve to solve the Dirichlet problem, and then in particular case, when you use a characteristic function of one of the boundaries, you are getting a so-called harmonic measure. So this is going to play an important role in the next. So far, we were dealing with these conformal maps between, let's say, complements of two intervals in the above picture and complements of two intervals in picture below on the left-hand side. But now we are going to map both of these pictures conformally to annular regions as presented on the right-hand side, where here C is a point somewhere in this annulus region, which is map of y naught, and y naught was map of infinity on the above. So here on the above left we have infinity. It goes to y naught on the left bottom, and on the right bottom it goes to C. Again, as one of our colleagues mentioned, he has studied this very intensively, and in his book on elliptic functions, there are also these formulas for these maps, again, very explicitly in other sources as well. So using these formulas, explicit formulas in elliptic functions of these conformal maps and of the green function in annular region, what we are getting, so these are the formulas. What we are getting is we can see what is going on in this Zolotaryov dynamics looking at annular region. So we are now deforming annular regions and looking what is going on when we in our left-hand side pictures with the form Pell equation and Zolotaryov polynomials. So there are two parameters, two integer parameters in parameterization of Zolotaryov polynomials is m and n. And if we just look through the formulas, which you have in this, for example, here is a book on elliptic functions, you see that what we are doing is where C is the point in annular region which corresponds to infinity, and H is the radius of inner circle. So we normalize our annular regions to be between a unit circle and smaller circle with the radius H. What we see is that this m over n, this is a ratio of two integers in our construction left-hand side. When you read it on the right-hand side, you get that this is ln c divided by ln h up to the sign. But in our construction, when we do this Zolotaryov dynamics, m and n are fixed. So that means that we can say that what we are doing, looking into this annular region dynamics, we can say that we are deforming c and h in a way that this ln c divided by ln h is constant. But then, looking into intrinsic meaning of that from the point of view of harmonic analysis, we recognize that this condition that ln c divided by ln h is constant actually tells you that in our deformation on the right-hand side of annular region and point C, we deform them in a way that harmonic measure is preserved. And now we can do a generalization. Now we can say, forget about m and n, forget about Zolotaryov polynomials. Let us transform annular regions, let us deform annular regions and the point in C in them in a way that deformed annular region and deformed point will satisfy this, that ln c divided by ln h is constant, meaning that harmonic measure is preserved. And so this is how we come to this important definition. So we will call deformations of annular region VH and point C inside, induced by variations of C and H, with keep this ln C over ln H constant. We'll call them the isoharmonic deformation because they keep harmonic measure preserved. So that means that actually we can say that our initial differential is actually the differential of the green function, and our condition that C1 hat and C2 hat are preserved is actually condition of isoharmonic condition on the complement of the union of these two intervals. So our result from a couple of years ago can now be reformulated with Vasilisa-Shamchenko, can be reformulated if the annular domains F, VH, and the mark point C, which can also be assumed that depends on H, deform isoharmonically, then the critical point of the green function of VH with pole at CH, which also deforms with H, provides a solution of Penlever-Six equation 1,8 minus 1,8, 1,8. Now, again, thanks to Achiezer and his explicit formulas, and explicit formulas given in his book, these formulas were derived before Achiezer, we can look at the formula for green function of annular region expressed in elliptic functions, and then calculate the critical point. And then when we do this, we are getting this new result, which gives us the new form of now solution, which is not necessarily coming from Zolotaryov polynomials and not necessarily from M and N, but any pair of intervals. We're getting this formula 13, which gives you a solution of Penlever-Six equation. So this formula is not new. This formula was derived in a seminal paper of Hitchin in 1995, where he provided for the first time general solution of Penlever-Six equation 1,8 minus 1,8, 1,838. But the derivation of this formula is logically completely independent of Hitchin's result. Of course, not knowing anything about Hitchin results, will probably not be motivated to study this matter at all, but at least in a logical sense, our derivation based on these isoharmonic deformations is completely logically independent. So I hope I answered to some extent to some of your questions. So, but now, you know, as we say in many languages, in some languages or in all languages, we have at least some concept of counting, and there is like one, two, and many, and this concept of one, two, and many fully is applicable here. So we saw that with one interval, we have trivial dynamics. We saw that with two intervals, we have non-trivial dynamics, and it's related to Penlever-Six equation. Now, what if we have more than two? What if we have three or more intervals? So many. Many means three or more. Then again, we can associate now hyperelliptic curve, and then with hyperelliptic curve we have associated Jacobian. But now hyperelliptic curve is not, of course, isomorphic to its Jacobian anymore. Jacobian is a high-dimensional torus, and hyperelliptic curve is still a curve. So we are losing this full match between curve in elliptic case and its Jacobian. What is happening now? And of course, you know, there is this important concept of Jacobi inversion. So if you fix now a point in Jacobian of a hyperelliptic curve, then resolving Jacobi inversion problem generically, you will get G points on the curve, which in Abel Jacobi map would be mapped to that point, fixed point in the Jacobi. And I will call, for the sake of this talk, I will call this generic situation. But for the sake of this talk, is very important this unusual way or constraint where we want to have to consider points in the Jacobian, which are Abel Jacobi map of a single point from the curve. And then after deformation of the curve and Jacobian, we want that this point still remains the image of one single point from the formed curve. And this is this new moment which comes with many. So in the case of two intervals, we didn't have this problem because there was isomorphism between elliptic curve and Jacobian. Here, many, or one, two, and many. So that means a situation of three intervals and more, or genus two and more, introduces this new challenge. This is how to do this constrained Jacobi inversion variation. But let me say first few sentences about this generic case. So in this generic case, a couple of years ago, Vasilisa and I extended this elliptic case and study of Penn-Level 6 equation to the study of Schlesinger equations related to this generic usual situation for curves, elliptic curves of genus 2 or higher. So in that case, we constructed a certain differential of third order, of third kind, and then with fixed periods, and then so here is the formula for this differential, and then we prove that these moving branch points need to satisfy so that these moving projections of the solutions of Jacobi inversion with respect to moving branch points need to satisfy this set of partial differential equations. And then we managed to, using this differential omega, we managed to construct solutions, explicit solutions of corresponding Schlesinger system with 2G plus 1 point. But now, so this is one slide which should give a sort of break and a sort of a naive explanation of what is going on. So what we did then, you can say that, okay, so here you have some parameter space. This black horizontal line represents a parameter space. Then you have, for fixed parameter, you have a given hyperelliptic curve. Above this red red parallelogram represents its Jacobian. And here you have our Jacobi image of this curve. And you can pick a point from this curve, Q0, map it to Z0, calculate its relative coordinate C1, C2 with respect to this lattice of Jacobian, given lattice of Jacobian. But then when you deform in space of parameters, you're getting a new hyperelliptic curve, you're getting new Jacobian, and this curve maps somewhere here, and this point Z0, with the point with the same C1 and C2 relative coordinates, will map somewhere. But in generic situation, it's not going to map on the image of the curve. And when you vary further, this is open condition, this point will remain outside this curve. So this is this sort of situation of generic, which we studied in 2008. What we want to do now is we want to study this constrained Jacobi inversion problem. So we want to now have, again, parameter space B. We have these two bundles, one with fibers hyperelliptic curves with fixed genus, and another with corresponding Jacobians. And now we want that we start with a given point, we map it to Jacobian, we read the C1 and C2, and then we start, and this belongs to the image of the curve. And now when we deform, we want that in the deformed Jacobian, point with the same C1 and C2 still remains on the image of the deformed curve all the time. This is the issue. From the billiard perspective, one can say that in the situation of two intervals, this corresponds to periodic billiards with an ellipse, and then you have a boundary ellipse, this blue one, you have caustic ellipse, this red one, and then you deform both the boundary and the caustic, but in a way that still in the deformed construction, the new obtained billiard trajectories are again five periodic. So this is that corresponds to the formation of Zola theory of polynomials. Now here, on this right-hand side picture, we have a symbolic, this is very schematic picture. This is in two, assume that you're in 2 dimensions, that you have these two blue ellipsoids, and these two red correspond to two confocal quadrics, which are caustics. And then, if you do this usual Jacobi inversion, and so non-generic case, what you get this sort of billiard order game. So in a sense, you're getting, because inverse image of 1 point in genus 2 of 1 point in Jacobian are 2 points on hyperelliptic curve, this will give you two quadrics which correspond to boundaries, and you will have a billiard order game which will go from one boundary to another boundary, then from another boundary to the first boundary, and so on, being all the time tangent to two given these red quadrics. And then the question is about deformation, how you deform these pairs of quadrics as boundaries and pairs of caustics in order that this remains periodic with a given period. But what we really want is to have the formation of a billiard within single quadric in higher dimensional space. So this is schematically represented here. Suppose that you have periodic billiard within one ellipsoid in d-dimensional space, or three-dimensional space if you wish as the simplest, and then you have two confocal quadrics and you have 4 periodic trajectory, and then you want to deform the boundary and these two confocal caustics, these red quadrics, in a way that this construction remains for periodic all the time. So in order to do this, we now need to go to Chebyshev polynomials over general Chebyshev polynomials. So Chebyshev polynomials over more than 2 intervals. And they will satisfy Pell's equation, where now this coefficient mu square is related to these endpoints of more than 2 intervals. And we can, using this affine transformation, we can normalize endpoints to be 0 and 1. And then now the question is, how can we deform these unions of 2 intervals, let's say 3 intervals? How can we deform them in a way that, let's say we keep 1 interval fixed, but we want this Pell equation to be satisfied all the time. So the theorem from Pechersdorfer and Schiffermeyer from 1999 tells you that if you keep 1 interval fixed, you can pick 1 endpoint of each of remaining intervals and freely independently vary it, while the remaining endpoints are going to be functions of these variables. So when we do this, we again, because of this Pell's equation, we again have this special function as we had before, and this, here denoted as S, and this special function guarantees you that point at infinity is going to be point of finite order. And now, so when we now do this sort of, again, sort of transformations as we did before, fractional linear transformation to normalize some of these, so to move infinity to, which is point of finite order, to a fine part to be point of finite order. After some very long and very non-trivial calculation, we come to the following part of our solution. We get that these dependent endpoints are going to depend on independent endpoints according to this law given in the box, and also this point of finite order, which is now in a fine part, is also depending on this moving free variables in this form, where the right-hand side is defined on this slide. So, and I will skip now this because my time is out. We can also generalize this from Chebyshev polynomials on support on union of D interval, which is support of Chebyshev polynomials to any union of D intervals. But what I want to say is we are getting constrained Schlesinger systems, which is a generalization, which is an adaptation of Schlesinger system, which corresponds to this situation where we have some variables which are independent variables and some variables which depend on them. So we are getting this system of constrained Schlesinger equations, and then using the constructions, the objects on this hyperelliptic curve, this differential omega, we are getting these quantities which give us the explicit solution. So here, this formula gives us, so I'm concluding with this theorem, which gives explicit solution of constrained Schlesinger system in terms of these differentials on, explicit differentials on the family of hyperelliptic curves. So this is the main result I wanted to present, which is still not posted, but I hope that Vasilis and I will post it soon on arXiv. And I will skip these things and come to this final few minutes as a sort of passage to the next session organized by Viktor Matveyevich Buchstaber. So let me say a few words about Boris Anatольевич Dubrovin. So I was strongly influenced by Boris Anatольевich, and I was fortunate and privileged to have Boris Anatольevich as my PhD advisor. And we all learned a lot from Dubrovin's brilliant expositions, from his talks and lectures, and in many personal contacts. And especially, of course, these last years of life of Boris Anatольевich, by the courage and energy he put in doing mathematics till his last breath. Boris Anatольевich gave us the last and the most fascinating lesson: his sense of fairness, justice, and measure, his gentleness and dignity, his hard work with a deep understanding of science, and at the same time, respect for the beauty and joy of life, and his profound understanding of music will remain in our memory and will be guidance for many. So here is one of photos of Boris Anatольевich Dubrovin. In Belgrade, he had a big family of his scientific grandchildren, and as a good scientific grandfather, he visited them or visited us a couple of occasions, several occasions. And this is him giving an inaugural lecture on the first Greece conference in 2008. After that, we had altogether 7 Greece conferences, but the first speech on the first Greece conference was delivered by Boris Anatольевich Dubrovin in Belgrade. Here is a second Greece conference in 2010, which was devoted to celebration of 60th anniversary of 4 distinguished Russian mathematicians. Here you see Valery Kozlov, Boris Dubrovin, Igor Krichev, and Anatoly Neistat. And thanks to Mitya Milyonshikov, we also got in possession of this beautiful poem of Anton Korchagin. So, excuse my Russian, I'll try to read it. Перед доской стоит Дубровин, невозмутим он и спокоен. Научным запылал огнем он неожиданно для нас. И сразу видно, это ас. Тут полились определения, и нет уже совсем сомнения в красе теории КДВ. For our colleagues from abroad, I made some very rough translation. And let me conclude by expressing, on behalf of all of us, the deepest condolences to Boris Anatolievich's devoted wife Irina and his beautiful daughters Dasha and Lisa. Thank you very much for your attention.
Thank you very much. First, let us now we finish with scientific questions. I think that there are some questions concerning your talk, but just before that, I would like to announce that just now, just after the end of this talk, we will have a small session concerning Boris Anatольевich Dubrovin with some photos and so on. And now let's return to the scientific talk by Vladimir. And are there any questions concerning?
Sorry, Vladimir. Isn't something parallel with you between your activity and the study of isoperiodic deformation? It was connected with the following problem, because assume you would like to construct periodic KdV solution, and you would like to keep the period. You, roughly speaking, you can shift for each gap, you can shift one end, and the position of the second end will be determined by the periodicity condition. Maybe something common with.
Yes. Peter, thanks for this excellent question. As I said at the beginning, I plan to come to Moscow this time. And one of my scientific tasks of that visit would be to meet with you and discuss that question.
Thank you.
So I think we can start to find a way to meet anyway and discuss this in our preprint, which is going to appear soon. We indicate your paper in a sense that as a sort of a related thing. So we already have your paper indicated, your activity indicated as something which is in that realm, how to say. But I would indeed like to meet with you and discuss this slowly and you know in person as if possible.
Okay, thank you. Thank you.
Mm-hmm. So just to so I think in spirit is very similar. Similar. And now the question is about further interaction and other. So and here I just to point out, since you asked, what we have here is at the end, my last theorem, we provide explicit solutions of this system of equations, which was something which was quite difficult for us to achieve and tedious to prove.
Well, other questions? Are there any questions in Zoom? No? Well, then let's thank the speaker again.
Thank you very much.
And now we shall proceed with this photo session and some memories of Boris Anatольevich. We need maybe 3 to 5 minutes technical break to organize photos. So we resume in maybe 3 or 5 minutes.
Ну это я не знаю, если мне даст, скажет, нет, это я не другое слово. И презентация просто на веб-слайде. Да, я даже не знаю, что сделать тогда.
Но у меня нет хаба просто. Вам, наверное, нужен будет поинтер, поэтому правильно. Давайте я сделаю так.
Мои слайды у тебя готовы. Ты сейчас, как я буду с микрофоном, и ты будешь искать как?
Я вам дам либо микрофон, либо вот это.
Давай
достать можно вот эти.
А достать можно?
Я Дубровин ставлю. Хорошо, Дубровин.
Я начал все забирать.
Ну, в общем, начать, наверное, с JPEG, а потом получится. Давайте. Вторым PDF, Пардон.
So we start our memorial session. I think that Viktor Matveevich will show us some and say some words about transcendentality.
Я очень рад, что в нашей конференции участвует столько много товарищей Бориса, учеников, коллег. Но вот сегодня я хочу показать подборку фотографий. И вот извиняюсь перед нашими иностранными коллегами, что я буду говорить по-русски, потому что я хочу передать эмоции. И вот фотографии, которые я покажу, они упорядочены по годам. К сожалению, первый год, который я нашел, это вот как раз 93-й год. Дело в том, что когда Сергей Петрович взял позицию в Мэриленде, он в свой контракт вписал, что он будет принимать учеников, коллег и, значит, с ними работать в течение этого. Ну, и обычно Сергей Петрович организовывал такие пары. И вот, значит, первая пара как раз была Дубровин и Букштабер, 93-й год. Он нас поселил в совершенно уникальном месте Seven Spring Village. И когда мы шли вот из нашего Seven Spring Village в кампус, ну вот нас сфотографировали. Так что это вот первая фотография 1993 года. Дальше. Да. А вот эта фотография совершенно замечательная. Она уже вошла в книжки, потому что это, смотрите, 1998 год, Эдинбург. Вот за нами это Максвелл. А все происходит в Эдинбурге, в Максвелл Билдинг. Дело в том, что 98 год – это год 60-летия Сергея Петровича, и было организовано 3 конференции. Первая, самая очень большая конференция у нас в институте, она очень широко была известна. Вторая конференция – это как раз вот знак признания его и его школы, была в Эдинбурге, это организовал Майкл Латья. И третья конференция уже была непосредственно в Мэриленде. И вот здесь вот вы можете увидеть Бориса Дубровина, он стоит с портфелем. И вот здесь вот Сергей Петрович со своей школы. Вот здесь совсем еще молодые. Видите, Искандер, Олег Мохов. Вот, а вот за нами, значит, Максвелл. Это 1998 год. Дальше. А это вот, смотрите, такой скачок. Я вам показывал 98 год. Вот, а это уже через 10 лет Сергей Петрович отказался организовывать конференцию. Он сказал, мне достаточно Новиковского дня. Вот там был доклад Валерия Васильевича, вот был доклад Бориса. Это вот 3 июня 2000 Новиковский день в Стекловке, где вот Борис делает доклад. Дальше. Смотрите, какая фотография. Но это вот он слушает докладчиков. Дальше. А вот это очень интересно. Обратите внимание, ГДИС. Это же вот то, что мы как раз вот с Валерием Васильевичем говорили. Это Geometry, Dynamics, Integrable Systems. Это вот замечательная конференция. Вот Борис, значит, организовывал ее Влад Драгович. Ну и Борис вот делает доклад. Дальше. Вот он как раз с Владом, которого вы хорошо знаете, который у нас часто бывает в Стекловке. Ну вот они, значит, учитель и ученик. Дальше. Вот как раз на этой конференции Борис делает доклад. Дальше. Дело в том, что эта конференция была организована на самом высоком уровне, руководство Академии, и вот видите, в национальных костюмах вручают. Вот, Валерий Васильевич, помните, как это все было? Замечательно было все организовано. Дальше. Ну это вот я хочу обратить внимание, вот видите, Ира. Вот это тоже вот на этой же конференции, вот Ира. Вот они, значит, с Борисом во время брейка. Это вот, да, дальше можно. Это вот дальше уже он беседует. Тоже 2008 год. Дальше. Тоже вот. Это все вот снимки. Дело в том, что по поводу этой конференции сейчас в интернете можно найти очень много фотографий. Они молодцы, выложили фотографии. Дальше. А это вот он у нас 10 ноября 2011 года выступает на общеинститутском семинаре МИАН. Вот можете тоже посмотреть. Вообще у меня такое желание сделать хороший альбом и подарить Ирине на память. Потому что я думаю, что это будет такой подарок в память Бориса. Дальше. Ну, это вот продолжение его выступления на общеинститутском семинаре у нас в институте. Вот минуточку. Ну, дело в том, что те, кто из нас бывали в Обервольфахе, прекрасно помнят вот эту самую, ну, как ее назвать, скульптуру, что такое. И вот, в частности, вот в 2012 году и это Борис был. Вот это, как говорится, этот фон у многих из нас есть, сразу узнаешь, что это происходит в Обервольфахе. 2012 год. Борис еще, вот видите, как он видит. Дальше. А это вот как раз вот то, что будет показывать Дмитрий Владимирович. У нас же Борис был руководителем лаборатории имени Николая Николаевича Боголюбова. И была организована конференция «Алгебраические структуры в интервьюерных системах». Ну вот, значит, как раз, как вы видите, это МГУ, по-моему, 1610, да, видите? Вот очень живая тоже фотография, она остается в памяти. Дальше. Ну это также вот. Дело в том, что вы можете посмотреть вот тоже. Я вижу Андрея Миронова, Олега Мохова. Ну, можно так увидеть наших участников. Да, да. Вот Андрюша Погребков, по-моему. Да. Дальше. А это вот следующее. Дело в том, что, опять-таки, это была не конференция, опять Новиковский день в 2013 году. Вот это одна из таких, вы знаете, что Борис потом тяжело заболел. Это одна из таких последних фотографий, но тем не менее будет еще. Это 2013 год, вот Борис. Пожалуйста. Дальше. А вот это совершенно замечательная фотография. Посмотрите, все улыбаются, все довольны, как Борис хорошо смотрится. Дело в том, что в 2015 году Джованни Фельдер в Аскони, а Аскони, вы знаете, это в Швейцарии совершенно замечательный центр для проведения конференции, типа Обервольфаха. И вот была организована конференция, повторяю, организатором был Джованни Фельдер, Веселов 60. Ну вот мы решили вместе сфотографироваться, и вот посмотрите, как Борис здесь хорошо выглядит, на самом деле. Вот я вот смотрю на него, это вот дело в том, что, как вы понимаете, 2015 год, а в 2020 году мы хотели отметить Веселову 70, но в результате это была конференция по Zoom. Вот так вот не удалось всем собраться в хорошем месте, ну и поздравить нашего коллегу. Это вот как раз Аскона, Швейцария, 2015 год. Дальше. А вот теперь уже буквально несколько фотографий, потому что мы не нашли года, но вы прекрасно знаете, что много лет Борис возглавлял вот СИСу, и СИСа нам представила вот такие фотографии, почему-то не смогла представить года. Поэтому посмотрите, пожалуйста, вот как он остался в памяти СИСы. Вот тоже видите, это сиссы. Это все, это материалы из сиссы, да. Посмотрите, какая фотография. Ну, я не знаю. Борис. Вот тоже такая фотография из сиссы. Посмотрите. А вот это уже, как я уже говорил, про лабораторию геометрических методов математической физики имени Николая Николаевича Боголюбова, которая организована на базе нашей кафедры в МГУ. И вот Борис читает лекцию. Насколько я понимаю, как раз в аудитории лаборатории. Правда, Митя? Что вы летняя школа. Но тем не менее, Борис был именно идейным руководителем. Он принимал участие и в формировании программы, и лекций. Дальше. Пожалуйста. А вот, пожалуй, вот это уж точно это, в самой лаборатории. Посмотрите, это вот Борис сидит за своим, у него был собственный кабинет. Видите, какой громадный компьютер, замечательное кресло. А это сотрудники лаборатории. Вот наш Сережа Смирнов и вот, значит, Троицкий. Вот они, значит, обсуждают. Но это, повторяю, это кабинет Бориса в лаборатории. Дальше. А вот это, к сожалению, последняя фотография. Я ее взял из журнала Letters in Mathematical Physics. Вот даже номер указан, страницы. Вот у кого есть желание, могут эту статью прочесть. Это буквально, довольно быстро после того, как Борис от нас ушел. В журнале Letters in Mathematical Physics появилась статья о его вкладе в науку. Вот это, посмотрите, как он на нас смотрит. Спасибо тебе, Борис. Вот это Саша предложил мне продолжать. Вот у нас сейчас будет вот такая же демонстрация и комментарии Дмитрия Владимировича Миллионщикова, который, в общем, организовывал, помогал и очень много сделал для функционирования вот той самой лаборатории на базе мехмата.
Спасибо за эту возможность. К сожалению, я поздно узнал о такой возможности, не очень хорошо подготовил слайды, поэтому их будет немного, но я постараюсь, мне кажется, они важные. Две основных идеи с выступления хочу. Первое – это свои студенческие годы. Тут вот, на самом деле, многие из нас, Володя Драгович тоже учились или на одном курсе, или на соседних. И для нас Дубровин был, прежде всего, мы воспринимали как один из самых лучших лекторов на мехмате, потому что мы уже знали, чьи лекции, на которые нужно ходить, которые можно пропускать. Но вот лекции Дубровина всегда было уже тогда ясно высокий уровень, высочайший класс лектора и докладчика. Конспекты, я уверен, все хранят, кто писал его лекции до сих пор, поскольку это всегда было очень четко и прекрасно. Ну и я потом хотел показать еще какие-то старые методические пособия, которые, кажется, уже лет уканули, но они до сих пор используются, и лучше некоторые подготовки студентов нет. То есть его вклад в подготовку студентов в мехмате длится на самом деле многие годы. А вот эту вот книжку, которую мы сделали, как вы видите, 6-я летняя школа по геометрии и мат-физике, тогда мы переехали в Красновидово. Вот что я хочу главное, то, что живет лаборатория, спрашивает, она еще есть? Да, комната есть, но мы как бы уже на общественных началах, у нас нет главного звена Бориса Анатольевича. Но вот главная вещь, которая от него осталась, то, что он нам завещал, то, что мы стараемся, ну, то есть вот в этом году я благодарен Дмитрию Валерьевичу Трещеву, который поддержал эту идею, он и выступил там, и был, и активно участвовал. Вот. Причем в разные моменты разные нам организации помогали, но, так сказать, первый импульс, данный Борисом Анатольевичем, он жив. И вот то, что, почему важно Красновидово, вот я хочу сохранить, потому что вот все помнят вот эти, одни из первых школ, которые Андрей Николаевич Колмогоров проводил, Красновидово знаменитые. И вот это, мне кажется, то, что снова Красновидово летом проходит школы по, ну, пускай, по такой более-менее узкой теме, но вот это очень важно. Но я не знаю, мне кажется, в этом году, к сожалению, я не смог быть, но мне кажется, всем понравилось, несмотря на ковид, это удалось живую провести. Спасибо Институту Стеклова. Так, можно там еще что-нибудь показать? Вот Владимир Драгович, я ему благодарен, с одной стороны, он украл главный алмаз из моего выступления, вот эту поэму, я ей хочу рассказать про ее историю. Дело в том, что, значит, вот эту богу, там Саша Буряк мелькнул. Значит, когда мы это все возобновляли, эти летние школы, тогда же ничего не было. Это так кажется, сейчас очень много конференций, они одна за другой идут, а вот 10-й год это была совсем другая эпоха. Ну и как это, что нужно было, как бы и студенты не знали. И вот после, я увидел, одна из дочек Аскольда Георгиевича Хованского написала впечатление про летнюю школу где-то в Америке. Я подумал, будет интересно, чтобы кто-то напишет про первую школу вот, Дубровинскую. И один человек спросил, а можно я в стихах напишу? Я говорю, так даже будет лучше. И он написал целую поэму, которая так и называется. Поэма о летней школе. Ну, естественно, она появилась в таком наивном стиле, не надо ее воспринимать как серьезное поэтическое произведение. Но как всякий такой эпос, Дубровин в этой поэме, видите, он фактически как былинный богатырь стал. Вот я считаю, что немного у математиков, в которых был создан такой искренний эпос. Вот можно, вот тут можно фразу дать, тут тоже любопытно. Видите, все фразы очень любопытные. И вот приехал к нам Дубровин делиться опытом своим. Он профессурой был любим за то, что было в нем немало того, на что равняться надо. За свой безмерный вклад в науку студентов не уводил он скуку. И вот тоже главная фраза, которая оказалась тогда. Всегда скупое на подарки и грандиозные зачатки правительство решило в раз, важнейший, подписав указ о том, чтобы щедро поощрить души чистейшие порывы, которые бывают ныне, а там вот сейчас вот, так часто трудно выполнима сложная рифма. И так Дубровин захотел создать ну, что-то вроде сказки. Ну, вот видно вот это вот рисунки тоже под стать поэме. Вот. Я хочу показать вот этот рисунок, еще следующий, который был у Володи Драговича. Вот я его, кстати, выделял, он у нас на постерах всех летних школ, я его ставил по разрешению автора Корчагина. Черт, больше нельзя там страницу. Так, вот это тоже Дубровин, видите. Все, Дубровин. Я уж не буду читать стихи, они, конечно, любопытны. Вот, видите, сколь стоит Дубровин, читатель знает уж о нем, невозмутимо спокоен, научно запылал огнем. Это уже вот все было. Веселов, видите, цепочки Тода. И вот картинку хочу показать снова. На самом деле она совершенно замечательная. Почему? Потому что вот там вот видно уравнение ассоциативности. То есть вот на мелкой-мелкой этой доске, вот если разобраться, вот эти ЦЖК-то видны. Ну и слушатели тоже, я уж не знаю, узнаваемы они или нет. Ну вот я не буду долго разговаривать, я хочу сказать, что воспоминания, они, нам без него, конечно, безмерно тяжело. И вот как на сегодня, то есть как-то мы продолжаем, но главное то, что если летняя школа, и я надеюсь, что не знаю, как Конгресс скоррелирует, но надежда и, так сказать, стремление есть и в следующем году вот те же сроки провести. Поэтому мы надеемся на Институт Стеклова, на замечательный математический центр, что вот и в следующем и дальше нам удастся эту важную традицию продолжить. Вот это вот, мне кажется, летние школы – это из педагогических живых дел Бориса Анатольевича то, что выжило, и то, что вот должно дальше быть. Вот, собственно, все, что хотел сказать.
Спасибо. Ну, вот, насколько я понимаю, демонстрационных материалов у нас больше нет. Вот, поэтому мы приглашаем продолжить это на 5-й этаж, 529-ю. Там уже...
Можно фотографию вот живого Сергея Петровича?
Ты кончил или нет?
Нет, я забыл, просто еще была хорошая фотография.
Поэтому, короче,
это вот Саша Буряк, вот у нас на кафедре сидят. Сейчас снимок.
Сейчас попробуем сделать.
Там вот есть такая фотография, где ученики Сергея Петровича, и там есть и Борис Анатольевич тоже. Вот я очень горжусь этой фотографией, потому что ее было очень трудно сделать. Во-первых, собрать всех учеников на конференцию, а во-вторых, чтобы туда в кадр не попали не ученики. Вот. Ну, я не знаю, куда удастся сейчас найти.
Есть сейчас.
Там вот большой такой... Нет, это как раз групповая фотография. Еще когда мы... Вот это летняя школа, видите, самое начало. Вот. Это вот, кстати, под редакцию Дубровина вышло 2 сборника лекций летней школы. У нас не просто все прошло, у нас есть все видеоархив, его до сих пор смотрят люди со всех точек мира, я знаю. Вот. И совершенно замечательно отредактированные 2 тома лекций лично Бориса Анатольевича. Изданы в виде файлов и так далее. Вот. А я еще, да, вот фотографии, которые хотел сказать, это юбилейная конференция Сергея Петровича, вот самый, видите, слева Борис Анатольевич. Ну вот, видите, совершенно замечательный такой коллектив учеников, единомышленников и как бы вот единая школа. Ну и все, понимаете, все это снято с Стеклова, что симптоматично, да, что интересно, важно. Вот, все.
Спасибо, Митя.
Виктор Матвеевич,
Здравствуйте.
фотографии.
Саша,
Можно я попробую показать фотографии? Я прошу прощения, что я это самое. Я вам послал какие-то, но я потом посмотрел, у меня еще есть какие-то фотографии, которые я хотел бы показать.
Так, а ты сейчас можешь показать?
Денис, да, а можно это сделать share screen? Нет?
Саша, спасибо большое. Давай,
Если можно, share screen.
Готово, вы можете делать share screen.
Ага. Угу. Сейчас. Давайте посмотрим. Видно вообще что-нибудь?
Видно. Так,
view. Давайте мы посмотрим. Так видно, да? Ну вот я посмотрел из ранних, конечно, Борю я помню, он как бы для меня старший брат. Я пришел к Сергею Петровичу, и Боря, и Игорь Кричевер были как бы мои учителя вместе с Сергеем Петровичем в интегрируемых системах. Вот. Замечательное было время. Но фотографий того времени у меня практически не осталось, хотя мы были очень близки. А вот, пожалуй, одна из первых фотографий, это вот это. Это, по-моему, кажется, 90-е годы, может быть, Европейский конгресс в Будапеште. Тут Сережа Натанзон. Ира, если вы здесь, вам большой привет. Сережу мы помним и всегда будем помнить. Тоже замечательное время. И Сережа был частью Сергея Петровича семинара. Вот. Это с Борей, мне кажется, это Будапешт, 96-й год. Значит, это Аскона, вот уже я Виктору Матвеевичу это послал, это действительно конференция, которую устраивал Джованни Фельдер, и это действительно была замечательная конференция, которая, когда все мы собрались и как бы и тут и все были, и все было замечательно, и Боря был душой компании, как всегда, и песни были, и походы были. Это вот Юра Берест, Сережа Смирнов, Боря, Паша Тингов и Ин Маршал над озером. Как там оно называлось? Это Аскона там вдали. Вот. Значит, здесь есть несколько фотографий, которые, мне кажется, Тамара Грава мне прислала, она, наверное, их узнает. А может быть, некоторые из них, я думаю, что это от Тамары я получил, но она, может быть, еще Миша Семенов делал какие-то фотографии. Это я просто покажу их. Вот Боря. каким я его очень хорошо помню. Вот, это вот как раз фотография, это от Тамары. Тамара слева стоит, Грава, это его ученики. Вот Боря, Марко Бертола, вот не могу я познать других. Вот. Боря был таким заядлым горнолыжником, известным тем, что он, когда мы катались, ну, мы там, если длинный склон, там всегда остановимся где-то. Боря никогда не останавливался. Он, значит, катил до конца, всегда на горных лыжах. Вот. Это вот опять на прогулке. Итальянское мороженое. Это с Ирой. Ира, большой привет. Большой привет. Это, опять же, ну, там есть какие-то фотографии еще, где я не сумел их разыскать. Боря, у него был замечательный бас, потрясающий бас. И кроме того, он мало того, что умел петь, он любил петь. И вообще ни одни конференции, все конференции, на которых он участвовал, всегда было пение. Вот. И, в общем, Боря приносил и песни, и у него был такой и этот самый, вот, и всегда было песни. Я помню, был где-то на одной из конференций, в Берлине, кажется, был такой хор, Боря, Коля Решетихин и Федя Смирнов. Это было потрясающе. Они, значит, вот, конечно, ну что тут говорить. Боре сейчас сильно не хватает конференции, мало того, что стали с пением плохо, да еще и ковид, конечно, сильно подкосил. Но Боря всегда останется светлым и вот таким вот веселым и очень оптимистичным человеком для меня. Я вот всегда его буду помнить. Вот, опять же, еще раз, Ире большой привет. Ну вот, пожалуй, все, что я хотел сказать.
Спасибо.
Виктор Матвеевич, у меня несколько фотографий нашлось. Алло.
Петя, ты давай, показывай.
Сейчас я тогда покажу фотографии. Все несколько штук нашлось, но тем не менее.
Давай, показывай.
Вот. Это, по-моему, 2002 год, Триест. Видите, тут, кстати, очень много, видите, знакомых. Ну, слева Борис Анатольевич, видите, и Франческа, и Павла, и Тамара здесь, по-моему. Саша Михайлов, Володя Соколов. В общем, вся честная, и Сергей Петрович в центре.
Алексей Борисович рядом.
Алексей Борисович даже. Все, в общем, говорю, вся честная компания. Это, по-моему, не пойму, это, по-моему, та же самая фотография или нет? Ну, близкая. И вот 3 фотографии нашел, когда я был в Триесте позже в гостях у Бориса Анатольевича. Это был уже 2007 год.
Петя, спасибо. Но ты послал фотографии, да, Петя?
Я сейчас... Нет, пошлю еще сейчас. Вам послать или кому?
Нет, я еще раз повторяю. Все фотографии должны быть у меня, потом я скажу на iPhone. Да. Я уже попросил Сашу Василова мне тоже прислали, так что просто так. Кто у нас еще может показать фотографии? Это очень важно. Нет больше? Максим Павлов, у тебя есть фотографии? Ты же много бывал там.
Виктор Матвеевич, у меня нету.
Жалко, жалко. Ну ничего, я думаю, что вот когда будет альбом, это будет наше общее достояние. Ян, у тебя тоже нет, да? Может быть, я не знаю. Все, если может быть, то ищи. Может быть, Значит, дорогие коллеги, мы приглашаем вас подняться на 5-й этаж, 520 этаж, правильно? 525 комнату, и там уже можно без фотографий поговорить.
At this point, we finish our Zoom session. So thank you very much.
Виктор Анатольевич, у меня, извините, у меня просто не было сегодня времени.